Ready. All right. Welcome, everybody. It's a great pleasure for me to introduce today's colloquium speaker, Professor Steve Tomsovic, who, of course, does not need much of an introduction because he's very well known to us as a long-term member of this department, but also through the excellent sequence of graduate lectures and classes that he teaches here. So Steve got his bachelor degree from Michigan Technological University in 1980, and a PhD from the University of Rochester in 1987. And then after that, he went to Paris in France, or close by there, where there's the Institute for Nuclear Physics, and he received a Junior Curie Fellowship to spend some time over there. And this started a lifelong association with what has become the Laboratory of Theoretical Physics and Statistical Models. After that, he spent 6 years at the University of Washington before joining WSU in 1994 as a professor, and he also became department chair in 2002 for a while. And so if you do the math, this actually marks his 30th year at WSU starting up. Yeah. So he has won many scholarships that allowed him to go back to Germany and spend time there as a researcher. So for example, in 2006, he received the Martin Gutzfeller Fellowship of the Max Planck Institute for the Physics of Complex Systems in Dresden. So the Max Planck Institutes are the most prestigious institutes in Germany in their respective fields. And so this prize allowed him to spend a year there and focusing on research. And currently, he just returned from another trip to Germany in Regensburg, where he did some fascinating new developments, some techniques for quantum many-body dynamics that he's going to talk to us about. Okay.
Thank you, Peter. Well, it's a pleasure to be here, and it's nice to be back. It was a great year in Regensburg in Paris, and I got an opportunity to start a new research line. And so I thought it'd be nice to share it with the department. So that's what I'd like to talk about. So first of all, controlling dynamical systems is an enormous subject, and you can imagine all kinds of reasons why you would want to control dynamical systems. If you're going to send a Voyager satellite out there, you want to make sure it goes by the planets you were intending to study, or all kinds of things like that. Or if you're a chemist and you're bringing reactants together, you want to control maximizing, say, the reaction byproduct you're looking for. So you can think of all kinds of things. And amongst all the things that interest me, chaos is one of my most sort of favorite things. In that case, there's a much smaller subfield called controlling chaos, and that was started by people like Kravoji, or these people in Maryland. And one of the ways of controlling classical chaos is called targeting. And so what we decided to do was to see if we could convert that into a quantum version. Like, can we make the closest analogy of what they did in quantum mechanics? And so that work's very famous. It's got 10,000 citations. It's huge, but no one, I guess, thought to translate it directly into quantum mechanics. And actually, I will go through some simple systems first, but we're really more interested in many-body systems. So that's what I'd like to talk about. So these are my collaborators in Regensburg. It's the research group of Klaus Richter. And interestingly enough, next year he'll be the president of the German Physical Society. So he's kind of starting to travel a lot and so on. But he's a longtime collaborator. And Lucas and Matthias are PhD students in the group, and Juan Diego is a senior member of the group. And the work I'm talking today will eventually show up in 3 different publications. So, but it's quite recent. All right. So first of all, if you want to control classical chaos, there's lots of different meanings to that. You can look up Ed Ott's Scholarpedia article or whatever and see even multiple meanings there. But I want to focus on targeting. And in targeting, you have a system at some point in phase space, let's say, the system's in some state, and you want to get somewhere else in phase space. So just think of this abstractly. And you may or may not have a specific time in mind. You want to get from there to there, and you know it's a chaotic system, and it turns out that what they came up with was a way of using chaos as a resource for being able to do this kind of control. So the idea there is, normally you think of chaos, well, it just thermalizes things. It just, it's hard. It's not something you think of control. You think of it as like the opposite. But actually, they came up with an idea in which you could think of it as a resource. And I'll talk about that a little bit. And I want to, they didn't use these terms, but I mean, it goes back to Poincaré and the three-body celestial problem in 1899 when he put out his third volume of celestial mechanics. But we'll talk about how you can use heteroclinic trajectories. So now we want to translate that into quantum mechanics. And so we're trying to make the closest analogy. So what we want to do is start with quantum states that are as similar to classical states as possible in order to translate the analogy over to quantum mechanics. Then you have to be able to figure out how to take advantage of chaos in quantum mechanics, where chaos doesn't exist in quantum mechanics because the Schrödinger operator is linear and all that nonsense. So there's that. And then there are additional elements in quantum mechanics that don't exist in classical mechanics, and you're going to have to deal with that one way or another. So then I'd like to talk about how this can kind of accelerate control. So I talked really briefly about a time scale. And then before I get to many-body stuff, I'll just pick a really simple paradigmatic system of chaotic dynamics, single particle physics, develop the analogy there, two different ways. And then once we understand that, then go on to the Bose-Hubbard model and talk about how we could apply these ideas to controlling many-body chaos in like an optical lattice or something like that. Okay, so that's the idea of the talk. So let's start with what is targeting. And the germ of the idea, or the precursor to the idea, came from Stan Ulam. He published a little Los Alamos report back in the 50s. And if you think about the gravity problem, if you just have two bodies in gravity, and one of the bodies is in a very elliptic orbit about the other one, I don't know, a comet and the sun, and you only have those two bodies, it really accelerates and speeds up as it goes into the sun, but then when it leaves, it just loses all that momentum again. Well, Ulam conjectured in the 50s, without a computer to test it out, I guess, he said, hey, the three-body problem's chaotic. If I have a really light mass object and at least three gravitationally interacting bodies, I could use that chaos to radically boost the momentum of the light mass object. And so that's kind of what NASA does when it wants to put out the Voyager or whatever out to large distances. It does these flybys, but if you only had two bodies and only two bodies were involved, you wouldn't be able to boost the momentum the way they're doing it. You have to have chaos. So that's sort of the precursor. And there was this satellite, the International Sun-Earth Explorer, whose initial mission was twofold. And somewhere over here, I forget how far, maybe a million miles, there's a Lagrangian point. So after they launched the satellite, the first mission was to be over here, moving with the Earth. It didn't have very strong communication power, so it had to be fairly close to the Earth. And it had all these instruments for studying the sun, and they didn't want the environment around the Earth messing with its measurements of the sun. So the first part of its life was over here, and then they kicked it into an orbit where it just elliptically went around the Earth like this, and it did all these. That was the second part, the Earth Explorer part. they wanted to study the Earth's geomagnetic tail and a whole bunch of other properties. So this satellite was getting old, it was running out of fuel. And this is around 1981 or 82. And the people at NASA had just told the American scientists who wanted to build a satellite and send it on a flyby to Halley's Comet in 86, they weren't going to spend the $10 billion to do it. And, you know, there was that sort of American, European kind of, you know, competition thing going on. So they built, you know, a satellite that was going to fly by and intercept Halley's Comet on the way. And so when NASA turned this down, this guy, Robert Farquhar, he got the following idea. If he made some small perturbations to the orbit here, he could set it up in such a way as this would fly past the moon, but only maybe 25 or 30 kilometers off the surface. And he could give it such a big kick in momentum that by just changing its speed a few meters per second, he could kick it into a sun-Earth orbit. And then over a couple of years, with almost no fuel, he could get it to meet this Giacobini-Zinner comet, which came before Halley's, and these guys were the first one to do a satellite comet flyby. So this is a kind of controlling chaos kind of idea where they needed to get to a certain point at a certain time, and they were able to do it with almost no fuel or anything. Now you can see from the dates, it took a couple of years, you know, because the comet didn't come till 85, but that's kind of the idea of controlling classical chaos and targeting. That's I think it's kind of cute. I mean, if you tried to just motor a satellite over somewhere, you need, you know, a ginormous amount of fuel to do that. But with chaos, you could just get there, but you have to be able to calculate the orbit. So, you know, if you don't, you have to, you know, that's the hard part is figuring out what orbit you need. So if we actually look at the Ed Ott, Verboji York, OGY technique, you know, if you make a small perturbation because of exponential sensitivity to initial conditions, you know you're going to diverge exponentially fast from where you're going. Now, in a conservative system, the opposite has to apply. If you ran that backward in time, that exponential divergence would have to be an exponential approach. Well, both things are always going on in a chaotic system. If you think about where you want to be, and you imagine going back in time, you would be expanding exponentially. But when you bring that forward, you can exponentially rapidly approach something as well in a chaotic system. So what you want to do is you want to use the exponential divergence for where you were going to go. So whatever this was going to do, and wherever it was, it's not where you want it. But if you make a tiny perturbation, you can get it exponentially far away. But if you can somehow intersect the thing that exponentially approaches this, then a tiny perturbation can get you exactly where you want to be. So that's how you're using the chaos as a resource. So I'll sort of show you a kind of abstract view of this. Well, maybe before I say that, if you take a double pendulum and you give it enough momentum so you're not just looking at small oscillations, and this is a picture of a double pendulum where they put a light bulb on this in the dark and they swung it and then just opened the shutter, and that's where the double pendulum went for a while they had the shutter open. If you think about it, you have to specify theta and theta prime, theta 1 prime, theta 2 and theta 2 prime. To get to all those places, that's a huge phase space. So a lot of times if you have many degrees of freedom, you know, if you want to get from one place to some arbitrary other place, this is an enormous volume of space that you're trying to explore. Well, because I want to translate this into quantum mechanics, I'm kind of coarse grain this idea. But if you think of phase space and you coarse grain it on the scale in which a quantum state occupies in a pseudo sort of phase space. If you think about Wigner's transform or lots of different ideas in quantum mechanics, you can come up with a kind of phase space, and the coarse graining due to quantum mechanics is that a single individual quantum state per degree of freedom, the volume it occupies is h, Planck's constant. So if you have d degrees of freedom, you would have Planck's constant to the d. If you divide that into a phase space volume, this would give you a dimensionality of a quantum phase space. So that kind of gives you an idea of how many states might be available to the system or that sort of thing. Well, that's going to be enormous if you have a lot of degrees of freedom. But the thing that's great about chaos is you go everywhere. Eventually, you'll go everywhere. So that's kind of the idea. Anyways, you can come up with estimations of how big the space is, so to speak, in terms of when we get to quantum mechanics. Now, let me go back to this idea of exponentially unstable and exponential divergence and convergence. Suppose you were here and you had a small deviation from this orbit. There's actually a direction which maximizes the exponential fleeing away, so to speak. Maximizes your butterfly effect. That direction is called the unstable manifold. And as you fly away, it goes wherever it goes. But the converse over to where, let's say, you want to end up is the opposite. There's this maximal direction of exponential approach to that point. These are stable and unstable manifolds that exist in chaotic dynamical systems. They're invariant structures. They intersect. So if they intersect, that means there's an orbit that from somewhere in the neighborhood of here, you got to pick it precisely, but it's at all times on both manifolds. So if you pick the right condition that hits this point 1, it'll then follow the other thing down to here, and this will greatly accelerate how fast you can get, or you can get to where you want to go. So the thing that's hard is, of course, you have exponential proliferation. If you make any error here, you'll miss this point. So the zone in the neighborhood of that heteroclinic orbit, that's called a heteroclinic orbit. That's what Poincaré was talking about in 1899. The zone around it is exponentially tiny. If I asked you to find a micron-sized bubble in the ocean, you'd probably tell me to drop dead. But it's there, and if you can find it, then you can get from where you want to be to where you want to go. So that's the kind of idea.
So on that map there, are 1, 2, and 1 prime in the system, or are those places where you are introducing a small kick to get on the trajectory?
Okay, so I said it's a schematic, but this is actually a stadium billiard, and this is a surface of section that's on the boundary. And so in this case, although it's a continuous dynamics, as far as this picture goes, it's a map, because you only plot the points when you're on the boundary. So it's not a continuous time thing in that sense. So this is a continuous manifold in the map, but when this point 1 leaves the boundary, it hits the boundary at 1 prime at the next point in time, or the next bounce off the boundary. So that's actually the stable and unstable manifolds of the chaotic stadium billiard. And points look like they're jumping discontinuously because you're only showing what's happening on the boundary, not the continuous time.
And to clarify, 2D picture makes it look naively like it has to cross, but that's actually a representation of a very...
They do have to cross in a bounded system. This is cool. This is infinitely long, this unstable manifold, and it cannot cross itself because then classical mechanics would not have unique classical trajectories. And likewise, so if you have a bounded phase space, you have this infinitely long line, that's an invariant set of points, But you also have this one, the stable manifold. If they intersect even once, they have to intersect an infinity of times. There isn't just one heteroclinic orbit, there's an infinity of them. So let's say in the case of the Giacobini whatever comet, I can't remember the name, you want to get there in exactly 2.5 years. You could find the heteroclinic orbit that gets there in 2.5 years. And you wouldn't, there's a minimum time. Maybe they could have got it there in 1.5 years. There's a minimum time, but after that minimum time, you could choose any of an infinity. Suppose they wanted it to get there in 4.5 years, they could have done it in, an exponentially proliferating number of ways if they had more time. So these manifolds intersect an infinity of times. That's a standard chaotic dynamics thing. So, and even in more degrees of freedom, right? Yeah.
So you pick your whatever time when you change the paths by minimizing the interview, or
Well, how we solved the problem of finding the orbits is a little complicated, and I kind of wasn't going to go into it really today. But the thing that's kind of interesting is if you consider the entire invariant set that's the unstable manifold and the entire invariant set that's a stable manifold, if a trajectory is a member of both, it's a member of both for all times, minus infinity to plus infinity. So you're never really hopping. Like you can, for intuition, you can say, hey, I went here and then did this. But in fact, you were on both manifolds at all times. And it's just a special set of discrete points with really, really exponentially tiny neighborhoods around them that will get you close to getting you close. Okay, so that's sort of the idea. Okay, so how does this help you? Well, if you think about continuous dynamics and you think about the volume a quantum state occupies, there's a minimum amount of time to get to an orthogonal state. And that minimum amount of time would be to get from this H-bar cell to the next H-bar cell over. Let's call that T0. Now, if you're just chaotically wandering around and you have these n cells you have to visit, if you just follow any old trajectory, it might take you to the end of the universe in time to get there. You have so many cells in this ginormous space, and H-bar is so small that just wandering around and trying to get there is really going to take way too long. So if, on the other hand, you go and you search for these exponentially rare heteroclinic trajectories, if you think about the properties of this unstable manifold expanding at an exponential rate, and I put in the KS entropy, which is the sum of all positive Lyapunov exponents. For every degree of freedom, you can have another positive Lyapunov exponent, so you can sum all those exponentials. So you put in the KS entropy. So that's the single cell expansion rate. And if you ask, how long does that cell take to expand to all cells? Well, that's logarithmically shorter in time. And so the thing is, you have to pick the right orbit that goes to the right cell that you want. And if you do this, you can almost make the time it takes to get from one cell to any other cell independent of the system size, almost. But it's logarithmically shorter than what randomly wandering around along a chaotic trajectory would do. So you're actually using the special properties of this chaos to get you where you want to go infinitely faster, or in some sort of a sense, optimally faster. You can't get there any faster than this exponential rate, as far as I understand. Okay, so if we want to make the closest analogy to classical targeting, then what we'd like to do is start with minimum uncertainty classical or quantum states. And so if you're thinking in ordinary Schrodinger mechanics, that would be like a wave packet, a Gaussian wave packet. You can make the delta Q, delta P be H bar over 2. That's your most classical object. If you're thinking more like bosons in an optical lattice, or photons, you're going to think about coherent states. And then these are minimum uncertainty field states, and you can also see there's a way to see how those are minimum uncertainty. So we want to start with a state like that, and then try to end, just in order to start in the subject and make the quantum translation of the classical things. Then I won't really talk about this, but I spend a lot of time finding heteroclinic trajectories, so that I won't talk about that. But I use a stability analysis, and I know how to intersect stable and unstable manifolds and search for these trajectories. So let's just pretend we've solved that problem, even though it's a really hard problem. Well, after you've got that, then if you want a quantum state to follow a classical trajectory, it doesn't matter how minimum uncertainty you started out, it's going to spread. As you follow that orbit, you're going to have to somehow counter quantum spreading. Otherwise, it'll just thermalize. It'll just equilibrate, thermalize, go everywhere, and you'll find it everywhere. You won't find it where you want it. So this thing doesn't exist in classical mechanics. In classical mechanics, you can have a single trajectory. In quantum mechanics, you have to think of the state as an ensemble of trajectories. And so you have to control the ensemble, not just the single orbit. And so this additional feature is an absolute necessity if you want to do the quantum version of classical targeting. Now, in addition, we did not want to get into making measurements, weak measurements, whatever. We wanted this to be purely unitary evolution. And so we wanted this to be optimal in the sense of you find the best heteroclinic orbit, and coherent in the sense that there's no measurements, you're only applying unitary evolution throughout the operator. So that's what we did. Okay. So this is our schematic. Your uncertainty principle is why this blob is not a point. It's centered somewhere in phase, it has a mean momentum and a mean position. There is a direction along which you have your maximal exponential escape, your unstable manifold. And somewhere in the neighborhood is the initial condition of that heteroclinic orbit you want to follow. So the first thing you could do is just apply a translation operator, and there's a very straightforward unitary operator that's linear in the generators for translating a wave packet or a coherent state a little bit and mean in position or momentum. And then once you start following that, you're going to spread out. You're going to have to apply some kind of unitary transformation to relocalize it, so to speak, and then carry on and keep doing that. And when you get near where you want to be, you can make a last little time step. So this is our first attempt to make the closest analogy to the classical targeting, and that's kind of the schematic image we came up with to explain it. So now I'm going to pick a simple single particle system, and the one I'm going to choose, where does it say kicked rotor? Oh, there's kicked rotor. This has been a paradigm for chaos studies, and actually it's a paradigm for another reason. If you are studying classical mechanics and you go to action angle variables, the simplest idea of introducing resonances into your dynamics is like the pendulum. And so if you pick the pendulum, so you don't have the pendulum turned on all the time, it becomes chaotic. You start introducing chaos, and so you break the perfection of the resonance. You start to create stable and unstable manifolds, and you can make a transition from something that's integrable with resonances to chaotic systems. So that was why it started being used classically, and then they quantized it and said, hey, we can study the quantum transition from integrability to chaos. And then it turned out Fishman, Grempel, and Prange in the 80s mapped the kicked rotor onto the Lloyd model of Anderson localization. So this system was not only a paradigm of the chaos integrability to chaos transition quantum and classically, but it was also a paradigm in which a non-random system, there's no disorder. You know, the original Anderson problem, you put site disorder and all this stuff. Here you have a deterministic system, and they mapped it onto the Lloyd model of Anderson localization. And so in momentum space, it also exhibits Anderson localization and features like that in its quantum mechanics. And so a bunch of people have made experimental kicked rotors, and not surprisingly, ultra cold atoms and the way they can do quantum simulation with them provided lots of the experiments where they made these. And they were studying things like quantum diffusion or the lack thereof, or Anderson localization and things like that. There's also kicked rotors. I think if you take the N2 molecule, they can control it and kick them in a certain way, and you can make kicked rotors out of N2 molecules. And you can also do it with optical fibers. But anyways, it also exists in a funny sort of way as a experimental system. So what is a kicked rotor? Well, it's just a kinetic energy of a particle on a ring. And, you know, it would be, if you just had this term, it would be a pendulum, but you turn off that interaction except for delta kicks in time, and every integer time step, you kick it with the pendulum, with gravity or whatever you want to say. And that then you study the dynamics from, let's say, just before this kick to just before the next kick. So that turns it into a map. Those are the mapping equations. And I always need to know the stability analysis, but you end up with this stability matrix, which gets multiplied as you iterate more and more. And as long as K is about 2 pi or greater, it's a strongly chaotic system. If K is less than 1, the CAM theorem gives you boundaries and phase space and all kinds of stuff. So it's near integrable. But I'm going to go to values of K much larger than 2 pi. Okay, so then how do you quantize it? You construct the unitary operator of the map. For the time where it's free flowing on the ring, you just have an exponential of this kind for the kinetic energy operator, and then for the momentum kick, the cosine kick, you have this, and this product is the unitary propagator, like the flow K operator for one time step in the map. And then these are the matrix elements in a position representation, and we can create wave packets quite easily. So we have our system, and if I now say, I want to start with my most localized state with no momentum centered here, and I want to get as fast as possible to a different no momentum state over here. And remember, because you're on a ring, 0 is equal to 1. That's the same point. So think of that as a cylinder. So this half and this half, that's a single curve. So you just want to go from here to here. If I just start to iterate it, 1 iteration and then 3 iterations, it just completely goes ergodic. It's a chaotic system. You're not going to control it at all, right? So if you just follow the chaotic system, it takes 3 time steps, and you have all momenta and all positions in your quantum state. So that's what you have. But if you follow this iteration and then recompress the stretching that the exponential is doing, so there's a little shift, you do the kicked rotor dynamics, but then recompress the expansion, and you keep doing it, and then do your little translation at the end, and you follow this particular heteroclinic orbit. If you do it that way, then instead of what I just showed you, you start here, you go there, and you go there. And the phase oscillations tell you about the momentum. The position, this is in configuration space, so you can, if you really wanted to, not that you do, but if you looked at these values of Qn and Pn for that orbit, you would find that this coherent state follows exactly that heteroclinic trajectory when you do that. So all you had to do was eliminate the spreading to get that to happen. Okay, and then this is just to show that it gets better and better as H bar gets smaller. You can make this control perfect. So I don't think I want to talk about that because I think I'm running late. Okay, I want to go through this again because that contracting the spreading is probably not an experimentally feasible thing to do necessarily. And so that's a kind of impractical suggestion. So what instead we wanted to do is look for a second Hamiltonian that admits the same heteroclinic solution as the original Hamiltonian. So if you think about this, if you pick a trajectory that's a solution of one Hamiltonian, and you only look at that one trajectory, you can invent an infinity of different Hamiltonians that all have that as a solution. Now, if you took a continuous set of solutions, you can't do that. But if you only have one orbit, you can invent, or if you know what you're doing, an infinity of Hamiltonians that all have that as a solution. Amongst that infinity of other Hamiltonians, one of them will be stable, sort of locally harmonic around the orbit, and it won't spread. So in a sort of quantum simulation sense, instead of actually trying to unfold or undo the problems that quantum spreading give you, you just go to a different Hamiltonian that has the same solution that gets you where you want to be, but which has no spreading in it at all, and then you don't have to deal with it. So this is the second thing we did. And here's a dumb example. You take kinetic, you just take a free particle and you say p squared over 2m is my Hamiltonian. You take another one, p0 p over m. This one's linear in momentum, p0 is just constant. And if you start with the initial condition, q naught, p naught, they have the same solution. They're not the same Hamiltonian, but they have the same solution. But you'll notice their stability matrices are not the same. This one has nothing in it except the identity, and this one has shearing built into it. So in one case you have shearing, in the other case you don't, but they both admit the same solution. Anyways, that's a sort of a dumb example.
Is it unique what you're looking for?
No, I mean I could
You just have different models.
yeah, but the thing is you want to get as close to harmonic as possible. So you have your solution, and in the neighborhood of that solution as a function of time, you want your Hamiltonian to appear as locally harmonic as possible, because as long as it's harmonic, it's classical, there's no spreading. So that's eventually the idea. So if you start with a Bose-Hubbard model, you just have to look at how do you come up with that thing. Okay, so that's the idea. So for the kicked rotor, if you do this, this might not be obvious, but instead of kicking it with a cosine, you kick it with a variable strength that knows about the orbit and has some phase information in it. And then halfway in between kicks, you have a fixed strength kick, and again it has some phase information. If you just alter your kicked rotor to have this extra kick halfway in between kicks and do this, then if you start your wave packet in the right place, it won't spread. And you might not just guess that, like my collaborators gave me a lot of grief for just telling them that was it. But if you think about stability matrices, then and you know how to construct stability matrices, you just look for the solutions of that which are stable, and that brings you to solutions like that. So anyways, we have this modified kicked rotor, and you do the same thing, and The kicked rotor has curvature. Well, there's a cosine involved. And so what you want is a tangent, but there's curvature. So it turns out that this way of controlling is not quite as good. If it was just as good as what I showed you, these circles would remain circles as they propagate. So this is kind of like the momentum position uncertainty of the state. You start at 0, go to 1, 2, you're exponentially accelerating away, then you're exponentially converging towards, but the distortion away from circular is a measure of how badly I'm not quite getting the perfection in the stability, local stability. However, I know how to improve it. And if H bar is smaller, so if you make H bar 16 times larger, and you look at these inner circles, you see they're not as distorted. Again, as H bar goes to 0, this would work perfectly. But I picked a different orbit, a different K value. I found this orbit. I redid the last calculation. And again, if you follow this, it follows exactly that orbit. But now you can see some little imperfections, and you can trace those imperfections back to the fact that these shapes are not perfectly circular. So, and I know how to improve it. You can just add a higher harmonic in the cosines, and you can kill these distortions. So it's not a big deal, but that works. Okay, so now let's actually go to a many-body system, and the one I want to choose is the Bose-Hubbard system. You can find chaos in that system, and if you think of, let's just think of a simple four sites on a ring type problem. You have interactions between your particles on each site. I don't know if there's 4 dips there or 5. It's supposed to, it's supposed to have 4, but whatever. So what happens is you have a hopping part to your Hamiltonian and you have an interaction part. And the competition between the two can give you chaotic dynamics. Or in the mean field equations, you can get, kind of, it's not as strongly chaotic as we can make these simple paradynamic systems, but it's pretty chaotic. So we're going to look at this system and we're going to choose a parameter strength, this gamma, which is the ratio of the filling factor, mean number of particles per site, times the interaction strength divided by the hopping strength. When that's in the neighborhood of 1 or 2, you have chaotic dynamics. And that's a scaling parameter for the dynamics. And because I like to think in terms of canonically conjugate variables and observable variables in Hamiltonian mechanics, I'm going to actually use these Hermitian operators called quadratures, not the annihilation and creation operators. I'm going to use the mean field limits of those because Q and P are Hermitian if you do this. However, and it's just like position and momentum, but it doesn't mean that at all. Q squared plus P squared over 2 is the number of atoms on a site, and P over Q is the tangent of the phase of the field in each site. So it has a different meaning, but all of my intuition for classical mechanics is much easier to work out with these Q's and P's, including the complexification of classical mechanics. So I choose to work with quadratures. And so this is the system we want to look at and try to do what we were talking about. Your coherent state, a Glauber coherent state, looks like this. I don't know what I want to say about it. It's just that you act this operator, and this is normalized on the ground state, and it gives you a coherent state, which you label by Z, and the mean momentum and position are given by QJ and PJ. In your pseudo phase space. I guess I should say that normally you think that you have a fixed number of particles. You don't have an arbitrary number of particles. However, if you have a large lattice, the difference between the two isn't very big. But you can do this for each lattice site you have and then project out the total number of particles so that you do have a fixed number of particles in your optical lattice, say. And everything I say that applies to the coherent states will also apply to these number projected states in the Bose-Hubbard model, because you have a U1 symmetry in the dynamics. And because of that U1 symmetry, if I find one orbit, I can rotate all the coordinates, you know, like cosine, sine, minus sine, cosine. I can rotate and find the exact same orbit. And so I can take a sum of coherent states that turns into this projected state, and everything else works out perfectly fine. So those are the kinds of states we're talking about. And if you take the Wigner transform, so you want your phase space version of your coherent state, this tells you where you are localized in phase space, what density of mean field trajectories you need to simulate what's going on, if you want to do a mean field simulation, which in this case will turn out to be exact, but that's a technical point. So what's going to be our control Hamiltonian? Well, if you look at, well, it was 2 slides back. This Hamiltonian, the competition between these two terms is giving you the chaos. This is quadratic in the operators. And if you looked at quadratures, it's also quadratic, but this is quartic. So it's that quartic thing that's making your trajectory or mean field trajectories, stabilities chaotic. It turns out you can just replace n minus 1 by the chemical potentials on each lattice site, turn off the interaction. And if you choose time-dependent constants that are given by the chaotic trajectory of the Bose-Hubbard model, you've got your control Hamiltonian. And now it's quadratic. That's quadratic and that's quadratic. You're guaranteed that there's no spreading in your wave function as you evolve it. So your stability matrix will be perfectly non-spreading if you make that. So the question then is, how do you find your chaotic orbit, and then how do you set your chemical potentials on each site? And I'll let the experimentalists worry about that, because as a theorist, I could just put it in the computer and run the trajectories. I don't have to worry about that. So we're going to start with an orbit in which 2 of the particles, I've got a filling factor of 1 here, but 2 particles are on one side, or the mean number of particles there is 2. Then 0 and 0, and then 2. This is a density wave. Half the sites are filled, half the sites are empty. And then I want to go to just arbitrarily pick another state of the system in which there's a mean of 1 particle per site, but there's a pi-half phase difference. In other words, the field has momentum. It's circulating around the ring. Here, there's no circulation. The field has no momentum. It's a density wave, but it's not going anywhere. I want to find the chaotic orbit that turns it into a uniformly populated circulating ring, just for the heck of it, right? So we do that. And these are the chemical potentials you need for the 4 sites. And those are the actual chaotic trajectories that tell us exactly how to set the chemical potentials. And so we have everything. We got our control Hamiltonian. We found our heteroclinic orbit. Now we apply it to the system. And now this upper panel, that's the uncontrolled system. And this is the controlled system. And this point is telling you what the quantum uncertainty principle is telling you. The spread is related to, quantum uncertainty. And since this is uncontrolled, it's going to spread out and it's going to equilibrate, thermalize, depends on how you want to talk about it. Whereas this one doesn't. And so if you compare these evolutions, you see that the other one rapidly starts to spread. This is just going forward in time, but it's following the orbit. And so the upper one is what sort of equilibration or thermalization, what the chaos does to you. The bottom one is what the control does. So your quantum state at the end is exactly what you want. You've got a circulating set. So I have a couple of movies that show this, and it's sort of a repeat, but I just want you to see, because it's fun to watch animations. So this is what you just saw. You can see the spreading in time down here. And that's how the evolution goes. And that calculation has actually a truncated Wigner calculation, but it would be identical if we had done the quantum calculation. Now the quantum version, or the targeting version, is this one, and you can see it's following the orbit, and it slows down, speeds up, and it does exactly what that line guiding your eye shows, and it ends up exactly where you want it. And then here's another case we tried. And this one, this is a crazy, chaotic, but periodic orbit. It's going to go, and then it's going to end up back where it started. I don't think you would guess that orbit existed or that it was periodic, but that's a periodic orbit. So you can make it do periodic things as well. And then this is kind of cute. It turns out there's a mapping from the 1D. Oh, I gotta quit. I want to say this about the 2D lattice. That was a 1D ring, but you can actually map those 4 sites into a 2D lattice, and if you do it right, you can take that density wave and turn it into a whole bunch of little vortices. So here, this arrow, the length of the arrow is the number of particles on that site. So there's a bunch of particles here. There's no particles here. That's the density wave. Every other site is empty. Every other site is full. But the direction of the arrow is the phase of the condensate there. So they all have the same phase. By the end of this movie, each little square will have phases that go around in a ring, and they'll all be uniformly long. All the arrows will. So if I go down here and start this movie, I found an orbit that it's chaotic, it does crazy stuff, but when you get to the end of the orbit, you've got a phase relationship in which the 4 sites in your 2-dimensional lattice, it's like a discretized vortex. It's so, you know, I don't know. So anyways, that's all.
That again?
Huh?
Can you play that again?
You like that? I like these. They're sort of fun to watch.
You're supposed to make it spell out WSU.
We could do it. But anyways, that's a chaotic orbit, but it goes from a density wave to a whole bunch of little discretized vortices. And if you'd use the number projected state, these are all entangled and so on. But if you just use the Glauber coherent state, it's unentangled the whole time through that evolution. So you've maintained no entanglement. If you do the number projected one, it is, and we can do that as well. It's the same thing. And if you do quantum calculations, I think because I'm kind of over, I should just speed through this. So let me just go to the observations. You've got to deal with quantum spreading. So if you want to keep the original system, you're going to have to intervene at times to compress the quantum spreading. You can't get around that in quantum mechanics. But if you want to use the other method, then you're really doing a quantum simulation kind of a method. You're choosing a completely different Hamiltonian. It's not a small perturbation, but you can make the system follow any highly chaotic orbit in a stable way. And you can get from where you want to go to where you want to go in the fastest time possible for a chaotic system. The Bose-Hubbard system, because it turns out the way we get our control Hamiltonian, if we do it the second way, is perfectly harmonic. There's no spreading, and it's an actual perfect control Hamiltonian. And there's a lot of flexibility. We could do other things as well. Things we're thinking about is how to actually take sums of coherent states and introduce a control of quantum interferences between them, following different chaotic orbits that come close together and then diverge. We're thinking about how to do fermionic systems. If you weren't talking about the Bose-Hubbard model, there would be a real question as to how deep in the quantum regime you can go. The Bose-Hubbard, because it's harmonic, you could have as low an occupancy as you want, it still works. And there are things like robustness, which I didn't have time to talk about, where suppose you can't turn off the interaction perfectly. Well, you can adjust the orbit to compensate for that tiny bit, and you can actually make it more robust as long as you can characterize how close to zero you can get and things like that. Anyways, that's what I wanted to say.
Yeah, thank you so much for the talk. Time for questions in the back.
So in your modified Bose-Hubbard model, where you took the force experiment, you made a quadratic conjugation.
Yeah.
How does the frequency scale of the time dependent part compare to the frequency scale of just the ordinary?
So if you look at how fast the phase rotates in the Bose-Hubbard model on a site, that's that time scale of those oscillations. You can't transfer. I mean, there's a hopping time scale, and you have actually kind of two time scales. You have that phase time scale and you have the hopping time scale. And because you want a chaotic system, you've kind of made them similar. So there's that time scale. That's the time scale of the modulation and the control parameters that you see.
Is the hopping time scale?
Or the phase rotation time. I mean, if you look at these orbits, you can, here, the circles and the like to go from here to here, that time scale is when you go from there around, so it's.
You have to modulate it pretty fast. Like you couldn't, if the frequency scale of the modulation is slower than the hopping frequency, will you get that?
This was built for chaotic systems, and if the two time scales are vastly different, you don't have a chaotic system. So if you're in the extreme harmonic oscillator end where there's all hopping and no interaction, there's no chaos. Or if you have all interaction and no hopping, it's just Kerr Hamiltonian. So really you're almost forced, if you want to talk about chaos, to be in the regime where those time scales are competing, and that's what's giving you a chaos anyways.
Okay.
When you say the continuing results agrees with the full quantum calculation, it really means the control outcome. Right?
Yeah.
Because it's quadratic.
Well, yeah, because we're comparing to the controlled evolution. The non-controlled one has completely sort of going to ergodicity type evolution. It's not even remotely the same. But the orbit, that orbit you're following exists in that Bose-Hubbard system.
What's your motivation to find this time dependence of this time potential? How do you design it?
Well, we know exactly what to do as soon as we have the heteroclinic orbit. So we go to the mean field equations and we search for the optimal heteroclinic orbit. And then we use that orbit's properties to fix everything in the control Hamiltonian.
So when you do the mean field calculation, if you use this coherent state,
Yeah,
that basically breaks this UL symmetry, right? That state.
it does, but it's the same calculation if you do the number projected state, except that you have a rotation flexibility.
Well, yeah, sure, but for the coherent state, you do have a fluctuation in the whole part number, right? If you already know.
Oh, yeah.
It's sensitive to that. I don't know if you get any actual replacing due to the fluctuation in the part number and this stuff. No.
No, I mean, it's the control Hamiltonian because it's perfectly harmonic.
Oh.
You know, think of a harmonic oscillator and its position and momentum uncertainty. They all move in concert together because the stability analysis tells you that there's no shearing, there's no stretching. Yeah.
So, yeah, sorry, I always think about it. The original was Harvard, not the.
Oh, that just goes nuts. It just goes nuts, yeah.
Yeah.
Are there any questions online?
Oh,
I have one.
Okay, go ahead.
So I guess I don't quite understand what the rules of the game are. So in the satellite picture, you know, you have very limited thrust, and so it's clear what you can do. But it seems like you're just like arbitrarily manipulating these Hamiltonia.
but it allows you to determine a set of chemical potentials that would get you to a state. Imagine for some reason you wanted to get your system into a state of little quantized vortices. You had your two-dimensional array and you wanted to prepare your optical lattice, your initial state in that state before you did whatever experiment you wanted to do. This would tell you how to set up your chemical potentials, and you have to control each of the four. You have to label them right in the 2D lattice, and you have to be able to control the four independently. But if you could do that, then you could convert a density wave, which is something you can construct, into that, and then you could go from there. So
in this case, you're limiting yourself essentially to local potentials. Like, I mean, in principle, you could change the dispersion, or you could also hit the system with highly non-local operators and stuff.
yeah, well, the problem with the Bose-Hubbard model is the thing that controls the spreading is not number conserving.
Mm-hmm.
So, you know, like you have A dagger plus AA, then that's kind of annoying. So to really control the spreading, you have those sorts of things. So if you go to this more quantum simulation like Hamiltonian, you can still get to where you want to go. And all you have to do is turn off the interaction and calculate the chemical potentials.
All right, so maybe with this, it's time for us to stop. If you've got further questions, I'm sure you can just come down here. So that's thanks, Steve, again.